Alright, so our second video we want to take care of is making sure everybody's comfortable taking the measurements and doing the calculations for the experiment you need to do. So our experiment is to modify the mass of the bottle and measure how much time it takes to lift it up, and then compare how much power it takes to do that with how much electrical power is provided to the Lego motor. So first step, let's run one example here and take the electrical measurements. Now, as we did earlier, we set up one meter to measure current and 1 meter to measure voltage. We set the voltage up to be 9 volts, and that's going to stay the same, so we'll use that value. And then we're going to measure the current while this is lifting. Now, this sample is going to lift up and hit the bottom of the table. While it's lifting, we're going to watch for the current reading. And so this is the interesting part. We'll go ahead and watch closely here and see what happens. So, as we fire this up, alright, so I saw a couple of numbers there, 122 milliamps, 28 milliamps, and so either one of those numbers would be fine. So we know 9 volts, 128 milliamps. Let's run through the calculations for the electrical power, which is the input power. So input, alright, so this is electrical power. Alright, so we're going to do the other side here in a second. So on the electrical side, we had voltage provided, which was 9 volts. And we measured current, which is, the symbol is I, at 127 approximately milliamps. Now we're going to need that in amps, and so we have to do the conversion here. So that's part of an amp, and so it ends up being 0.127 amps. Alright, so electrical power is calculated by multiplying voltage times current. For us, that ends up being 1.143 watts. Now a watt is a joule per second, and so that's the units. Now let's take a look at the mechanical side. So I'll set this up again, lift it up a little bit, and then set it back down. We'll run this one more time, only this time what we want to do is, we know we're lifting 150 grams. That's what I put in this bottle to start with. You'll be varying that as part of your experiment. Now, how high are we going to lift it? We're going to lift it so that the top hits the bottom of our lift table. And so for us, that's about 51 centimeters. So we'll keep that in mind, 51 centimeters. And we'll be measuring how much time it takes for it to lift. So I'm going to power it up, and I've got a stopwatch going. And alright, so stopwatch shows 1.12 seconds. And so let's go ahead and do the mechanical power calculations for the output. Alright, so this is mechanical power. So what we've done is we've lifted a mass against gravity a certain distance, and we've done it in a certain amount of time. And so here's what we need to know. We know our mass for today is 150 grams. Now we need to have this in kilograms, so that means it's 0.15 kilograms. Now we're doing that work against gravity. Gravity is 9.8 meters per second squared. Right? This keeps our units working. And we lifted it at a height of 51 centimeters, or, in our case, 0.51 meters. Okay, so that's how much work we've done. Let's go ahead and calculate our work. So work is mass times gravity times height, which for us is 0.735, and that's in joules. So now the amount of time it took us to do that work we measured, which was 1.12 seconds, and now power is work divided by time. In our case, that's going to be 0.56 watts, or joules per second. So there's our power calculations. Now the next step is calculating our efficiency for this system. So let's go ahead and calculate that efficiency. And efficiency is power out divided by power in. In our case, we're talking about the mechanical work that we're getting done, mechanical energy, and we're putting in electrical. All right? So, and again, the symbol is an E, usually shown as a percentage. And so we're going to take our output power, which was 0.656 watts, and we're going to divide it by our input power, 1.143 watts, and then we're going to times it by 100 to make it a percentage. And so for us, our percentage is 0.574, or 57.4% efficient. So for each watt we put in, we get 57% of that out doing mechanical work for us. All right, so that's your primary calculations. The rest of the stuff will be covered in a PowerPoint on Angel.